Yes.
Okay, cool.
So we're the Akronauts rocket design team. I'm Emily Armbrust, the president this year. I'm a fourth-year aerospace systems engineering student at the university. And then I'll let John introduce himself.
I'm Jonathan Davis. I am about a third-year aerospace student. I'm a continuing education student. So 6 years in the Army, and then now I'm in the aerospace program here. So that kind of, my curriculum's a little wonky because of that, but yeah. I'll go ahead and pass it back over to Emily to open up the introduction.
Yep. Did you hit the next slide?
No, I can't. Oop.
There we go. So for just a quick agenda, we'll introduce the team and kind of what we are, give you this year's progress, a little bit of what's up next, and then a closing. And then on the left, you can see there's a picture of an old payload from 2 years ago at one of our competitions. So a little bit about the team. We're completely undergrad, and every year we design, build, manufacture, and launch high-powered rockets and their subsystems. We're comprised of driven students who desire to learn a lot about rocketry and anything like in the aerospace industry. And then actually on the left side, you can see one of our most recent subscale two-stage rockets that we've developed. The rail was actually for the first time built and assembled in my backyard, and then we put the rocket on it to like get the cool picture. So it's kind of funny, like my garage is in the background, but that's a little explanation on that picture, and I'll hand it back over to John.
Seemingly as a matter of fate, my cat has come into the room and decided, or maybe now she's a phantom. I don't know, but she came in and was very loud. So I apologize if she shows up and she's meowing. But yeah, so that's the introduction. And yeah, that rocket right there is projected to go to about 10,000 feet, stands 11 feet tall itself. And the portion that actually goes to 10,000 feet is the uppermost segment up in this region. So that's pretty cool. If you can hear her, she's going. We'll go ahead and take a moment just to meet the team. This is our executive board. You can see Emily, she's the president, and we have an executive board that consists of 7 students total. And then I'm down there as the safety officer for the upcoming year. But one of the cool things is that we have a pretty diversified group on our team. We have members from aerospace, mechanical, computer engineering, biomedical, computer science, really all over the place in CEPS. And then we even have nursing students on the team that are involved. And so that's pretty cool as well. From there, I'll go ahead and pass it back over to Emily to talk about team growth.
So despite what you may think, over the past year with COVID, our team actually grew a lot. And then with that growing of people, we decided to expand our leadership and how we're organized. So we're currently sitting at 26 positions that undergraduate students are filling in this next upcoming year. So we have 7 on the executive board. We developed a new position, systems managers of the 3 subsections of the team, which are propulsion, structures, and the innovative systems lab. And then we also have developed a new administrative branch that has marketing, which is split off into outreach and media, and then an environmental health and safety branch. But really the big scope of this slide is really the words across the bottom of the more people we have on the team, the more projects we have, the more projects we have, the more leaders we have, and then the more leaders we have, the more opportunity is created for these students to develop themselves and then further themselves into industry. So I'll hand it back over to John.
So with that, we wanted to go ahead and kind of touch on this year's progress. And so this is actually hearing you talk about women in engineering, Mina. This was one of our photos that kind of encapsulated that on our team. There was a moment where the team back in 2019 at the Spaceport America Cup was preparing the energetics, the black powder separation charges for deploying our parachutes. And in that moment, there was just kind of like this organic moment where not all, but a good group of the women that are on our team, who are actually, practicing women in engineering, we were able to get that photo. And so that was pretty cool.
Love it.
But,
nice.
Yeah. So from there, one of the biggest things that we accomplished this past year, it's actually pretty remarkable, and it hasn't really been done at our scale. And for us to be able to do it, it kind of grows the capability of the team in a pretty unexpected kind of way. And that's the modular systems development. And so modularity is a commonly used thing in industry dealing with high power rockets, or rather orbital rockets. If you look over at the picture on the bottom right, you see the Orion Crew exploration vehicle. I actually work up at Glenn Research Center on the European Service Module, which is one of the modules that's a part of that entire infrastructure. And so modular systems are really common. Other examples are like the International Space Station that was built in a modular format in orbit, the Hubble Space Telescope, that's a similar story. And then all orbital launch vehicles act as modular systems. At our scale, implementing a modular concept looks like the SolidWorks model that you see with the green bulkheads right there. And then above, you can see the parts that we were able to machine that allow that to happen. But what that allows us to do at our scale is improve vehicle design and complexity. This allows us to take motor modules that are using motors that are made commercially, or ones that we make ourselves, or even liquid engine concepts, which we'll talk about in a minute. It allows us to be able to integrate them into
John, you may have froze.
I think, yeah.
It allows for independent subsystem development. It allows no. I think I cut out there for a second.
You did.
Am I back?
You're back.
Okay. Is the presentation still there? I apologize. I don't know what happened.
Yeah, you were just
Okay.
finishing up on
yeah.
integration.
I guess what I was probably saying was just it allows for individual subsystem development. Our payload teams and our avionics teams are able to work on their individual systems and then integrate those into the launch platform. And then that also allows for vehicle integration to be much more seamless on actual launch days. If we have an issue with one module, we're easily able to replace it with another. From there,
So then
that kind of carries us into innovative systems, and I'll let Emily go ahead and kind of introduce that.
Yeah, so the other area we're expanding in is our innovative systems branch, developing more complex and advanced systems, such as, like you can see on the left, the drone. So that's a bay of one of the rockets we're developing right now, and it's aligned with that modular system. So there's a rotational module, the drone area, and then also like a kickstand module. And then on the right side, there's a system that was developed this past year called the Submerged Data Concentration Unit, which is kind of like a supercomputer in a fish tank. But that system was iterated over the past year with prototypes, and then finally came to completion, and the whole thing was successful. And the people we showed it to at the one launch were pretty impressed with the system in itself. And then the center is a little schematic of the flight computer that some of the students on our team are developing. So the goal is there to start building as much as we can in-house and have students learn by building their own rather than buying the components. But you can move on from there.
And so that carries us into looking ahead, what's next. That we kind of went over just what we've been able to accomplish even during the COVID pandemic. We honestly, at the beginning of the year, didn't expect our team to grow as much as it did, but it did. So looking ahead for what's next, this picture right here is the Spaceport America. This is in New Mexico, Richard Branson Spaceport for Virgin Galactic, and this is where we go for our Spaceport America Cup. We actually get to tour the facility and see some of their things. It's pretty amazing. But looking at what the team is getting involved in, there are three main things that we're targeting moving forward, and each one of these is individually very exciting. The first is the I Promise project. This is our two-stage demonstrator. This vehicle is actually a two-stage 30,000 foot apogee vehicle. It's all fiberglass and aluminum construction, and it has a Mars terrain mapping mission for the payload. And that's where that drone comes in. That drone's outfitted with a LiDAR sensor and is able to map the terrain. That's actually also our largest outreach initiative to date. It's actually a partnership with the I Promise School and the LeBron James Family Foundation. They've given us their blessing to put their logos on the rocket. And after we launch this vehicle and recover it at the launch in New Mexico at the Spaceport America Cup, we are actually going to be donating that rocket to the school to display in whatever format they want to, whether they want that to be in their foyer or elsewhere, for the students to kind of gain insight into the world of rocketry. And we're actually working with the students to develop their own rocket team at their school. So there's a lot of really cool things going on there. But from there, we also have the Emergence series that we're developing. This is our high altitude series. This has to do with our own solid motor development and advanced vehicle design. We're targeting over 100,000. It looks like I have a typo right there. Forgot to add a 0. But we're targeting over 1,000 feet by 2023. We have a 10,000 foot shot with Emergence 1 actually coming up relatively soon. Hopefully there will be a launch somewhere in the summer time frame. And then we're targeting the 100,000 foot launch by 2023. We have a 30,000 foot one that's not included here either. That one's in the upcoming fall time frame. But then we're also targeting a space shot by 2025. And by space shot, there's only a very select number of organizations at colleges that have successfully achieved this. And we're hoping to be one of those. A space shot means reaching the Kármán line. And so that's what we're targeting there. And that's the Emergence series. And then after that, we have the Venom 4 engine. Venom stands for VAPAC Ethanol Nitrous Mark IV. It's the fourth iteration of this design concept, and you can see a picture of it above. It's outfitted pretty well, looking nice. We have safety approval and a lot of support from the College of Engineering and Polymer Science to pursue this project. We're even getting to the point where we're beginning to have manufacturing and testing locations, so that's really exciting. But the VAPAC stands for vapor pressurization. It's where we're using the oxidizer's vapor pressure to pressurize the whole system. It's pretty challenging engineering ideas there. The fuel is ethanol and the oxidizer is nitrous, racing grade, typically used in automotive application. And then we're targeting a flight of this engine by 2023. And so these are the three main projects we have coming up in the short term, or well, short to long term, I suppose. From there, this kind of just, it's a little detailed. The main thing that I wanted to communicate with this slide is just that we have a quarterly breakdown of things that we're trying to accomplish in the upcoming academic year. And the main thing that you can see is at the top, the Emergence series going across. We have Emergence 2 and Emergence 3. Those will actually be two things that happen in the upcoming academic year, the flight of Emergence 2 and the further development of Emergence 3. And then the Venom 4 engine is a year-long project, and the I Promise project is all through the year as well. And that, the I Promise project, there's something that we're trying to do there. If you see right here, if you can see my mouse, this 152 millimeter O-class motor, the largest class motor we've made to date is an N-class motor. We're moving into the O-class, and the reason why that is really cool is because MIT, their rocket development lab, they have a P-class motor, and so we're inching closer and closer to that level of production, and that's really exciting for us to be able to compare ourselves to those groups and show that the University of Akron has students that are capable of achieving the same feats, and so that's really exciting for us. But the I Promise project is all through the year, and there's a lot of really cool things inside of that. But from there, I'll go ahead and pass it back over to Emily.
So in summary, with the way we've developed over the past year and then moving forward, our big things are team growth, creating as much experience as we can for as many students as we can give it to. Sitting right now is with 26 students in leadership, and then hopefully growing the number of members. And then further developing our vehicles through the modularity platform, which expands our capability to bring different types of projects into the rocket and then furthering our projects, expanding in propulsion from solid to liquid engine, moving into high altitude shots, and then also developing higher levels of innovative systems. And then, as always, the Akronauts and their vision is continued dedication to student development and achievement at the highest level. And then with saying that, can move to the next slide. So with the whole Akron experience for students in the College of Engineering, there's the 3 pillars of curriculum, design team, and co-op. And I see involvement in design teams like the rocket design team is really vital with further developing students as they use their theory and math skills that they're learning in their curriculum and in their classes, and then applying them in that design team setting where they can dive deeper into those concepts, really looking into their textbooks, and then also applying those in more hands-on manners, like actually going in the machine shop and manufacturing things, building a rocket from start to finish and seeing the whole system through, while also developing communication skills, leadership skills, team building skills, and then utilizing everything that they're learning on this design team and applying what they're learning in their curriculum to interviews where they're talking to companies for co-ops, and then utilizing everything that they learn in this undergraduate setting of co-op curriculum and design team to give themselves the best platform to jumpstart into their full-time positions and hopefully getting those great jobs right upon graduation.
So from there, we just want to thank everybody for sticking around to hear us go through our spiel. Hopefully it was cool, enlightening, maybe gave a lens into one of the student organizations that maybe wasn't there before. And we'd love to take any questions if anyone has any.
Well, I just, for one, I'd like to say I appreciate your presentation. You guys did a great job. Again, we'll open the floor up. Anybody have any questions for the Akronauts team?
Emily and Jonathan, very impressive. So this is Steve Johnson. So this looks like a fairly expensive endeavor. How is this all funded? And do you raise that, or is the college providing that, or?
It's a group of different sources. Every year we develop a proposal for our budget to the university. And then on top of that, we also gain funding through sponsors. So we reach out to different companies around either Akron or even like further than that. So we have different alumni even that even give us different amounts of money. And then the cool thing with alumni is sometimes that they donate and then their company will match that amount. So one of our really big alumni this past year that contributed to the team was actually Victoria Jackson. She works for Raytheon currently out like in Kuwait, and she donated $5,000, and then her company matched that, and we got $10,000 from her pretty much alone, which was really cool. So having the connections through our alumni and sponsorships for like us reaching out, along with the university support, along with like asking for donations, like on a smaller scale level of just like material and such. But it is kind of like run like a mini business where we have a budget and we have to break it down into the sub teams and then work out what we can and can't buy.
What is your annual budget?
You want to answer that? You want me to go?
You can go.
Okay. Well, historically, our annual budget was maybe somewhere between $20,000 and $40,000. Before the COVID pandemic, there was a higher contribution from various sources, but going through the COVID pandemic, everybody being impacted in the way that they were, some of our budget this past year especially definitely went down. We were lucky in that last year we prioritized the idea of making sure that we kind of had a savings account in case something happened, and we were always talking about frugality, and that kind of led to us having a reserve for this year. And then Victoria gave us that huge boost, and that helped. And we were able to get a couple grants through the college. So this year, our total working budget on the year has been about 20,000, which is less than what it's been in the past, for sure. But the biggest thing is that the other thing about the modularity concept is, you know, people are really impressed with SpaceX's ability to reuse rockets. They land them, they refurb them, they launch them again. What modularity allows us to do is individually develop modules, and specifically propulsion modules. And so what we're able to do now is we can make a solid motor module and attach it to our rocket, or we could remove it and develop strictly a liquid engine module and attach that to the rocket. And approaching our projects in that fashion and prioritizing reusability in our projects moving forward has actually made it to where we've been able to reduce our budget, or like our expenditures, and prioritize spending in other areas like the development of flight computers and things like that. So in short, it's been typically, I would say on average, probably about 30 to 35,000. This past year it was lower, but we've come up with innovative solutions to deal with that situation.
Yeah, it sounds like an awesome program, and I'll reach out. Reaching out to the email that's on here is the best way to get a hold of you guys.
100%.
Yes.
Okay,
You
cool.
Akronauts.
Yeah, it was great. Sounds like an awesome program.
Thank you.
Where do you guys fly these things? I mean, get above 2,000 feet. Now you're into civil airspace and what have you. You can't just go launching that out your backyard, right? That's
No, you can't, unfortunately. So there's a location down in Southern Ohio, Springfield specifically, called Tripoli Mid-Ohio. And actually every like 2 weekends, there's just like a group of like rocketry gurus that get together and launch their own model rockets. And it's open to different universities to come and like fly. But there's a ceiling of, I think, 15,000 there. So if you go anywhere higher than 15,000 feet, you do have to go out west. So the bigger rocket on one of the earlier slides was flown out in California at FAR, which is Friends of Amateur Rocketry. And that's another group of people that host different events where people can fly rockets or do static testing. And then our Spaceport America Cup competition is out in New Mexico, specifically like Truth or Consequence area at Spaceport. So that's another location where we've flown.
Yeah, we basically just have to find a vast, expansive space with no humans. And so that tends to be the desert, or occasionally you'll find a cornfield in Ohio.
Of all the rockets you've launched, have you been successful in returning them to your target location?
When you say returning them to a target location, do you mean guided recovery during their descent?
Yes.
So we actually have a team that's working on that. We have a parawing concept that uses servos inside of the rocket. There are these winch servos that are pretty powerful, and they're meant to control a couple of the shroud lines that go up to the wing that the rocket is descending under. That project is currently under development and is actually being prototyped right now. There's going to be some testing coming up where our recovery team is attaching it to a giant industrial fan and, you know, inflating it and then trying to gauge how much they're able to control it and how much rotation of a servo kind of deflects the flight pattern, things like that. So there's going to be a lot of like mathematical expressions and equations to represent whatever that system is doing. But in short, I mean, it's being developed right now, and that definitely is a goal. We haven't done it to this point, but we do have the systems available to return our project safely, in that we have a drogue parachute. We use dual stage deployment. So at the apogee, the highest point of the rocket's flight, we'll have a small parachute come out that we call the drogue, and that slows the vehicle down so that its terminal velocity isn't too high. Because if it was too high and we didn't have that parachute come out and then it just came down kind of ballistically and then let a parachute come out, the big parachute would tear apart the rocket frame and you could end up injuring people. So we slow it down with the drogue parachute, and then that keeps it at a speed where we can open the larger parachute and not have it drift too much. Some teams will make the mistake of having their large parachute come out at apogee and then it floats like 5 miles away, and that's always a terrible experience. and you always see people just absolutely mortified when it happens. So we have checklists and procedures to try and make sure that we never do make that mistake.
Thank you.
Mhm.
Okay, well, I really appreciate you guys coming by and giving us an update. It's very well done. I really appreciate it.
I would like to add that this is Bob Handelman. Both of you are very, very articulate in presenting this. I learned a lot. I have a grandson who's a graduate of the University of Akron Electrical Engineering, and he's working on the propulsion system up at NASA here in Cleveland that's going to send the rocket that goes, after it goes to the moon, that send the rocket to the Mars, and he's working on that. So I don't think of the University of Akron in terms of space, or I didn't, but I do now. So thank you.
That's actually awesome to hear, by the way, because just as I guess a caveat, quick shout out to some of our team members. Emily and I actually work at Glenn Research Center. I work in propulsion. She's worked in the testing facilities. She's coming to my group this summer. We're going to get to work together, her full-time, me part-time, and we're working on the European service module. So the propulsion system taking the astronauts to the moon, which is really cool. And then we have a couple other people on our team who are Pathways interns at Marshall Space Flight Center and Johnson Space Center, and each of them are moving into propulsion as well. So that's really cool to hear that Akron's sending people out there like that. Our vision is using this team to create a space mecca here at the University of Akron. That is 180% exactly our focus. So we're pretty obsessive about it, and thank you very much.
Well, you're welcome. I'd have to ask Ethan's permission, but maybe he should show up at one of the meetings or something. Maybe being an Akron U graduate, he has an intense interest in the University of Akron and was very active when he was there.
That would be amazing.
Yes, that'd be awesome.
Well, thank you guys again for stopping by. I really appreciate all the effort and all the good words about the college. I really appreciate it.
Of course. Thank
Thank you
you.
for having us.